Okay, so I want to link rational numbers to rational expressions. So raise your hand if you remember this. How many of you have seen that before in school at some time in your life? Good. Can anybody pinpoint? Somebody in the last class knew exactly which year it was. Good job. 7th grade. Good. Yep, 7th grade. Okay. So in 7th grade, you learned about the natural numbers. Those are that you can count on your hands. 1, 2, 3, 4, 5, right? Then there's the whole numbers that include 0, or the one that's got a hole in it. Then there's integers. Whole numbers are 0, 1, 2, 3, and then all the other numbers. So it includes all the natural numbers plus 0 are the whole numbers. Then integers includes all of the positives and the negatives. And then rational numbers are anything that you can write as a fraction. Okay? So anything you can write as a fraction. So can you think of something that you can't write as a fraction? You can't. Mixed numbers? Oh, the one with the line above it. So anything that's repeating, good. No, wait a second. If it's repeating, that can be used as a fraction. Philip, we got to clear this up. So if it's repeating, isn't that 1/3? Yeah. So the other way, what's the other way? If it keeps going, but it, okay, why is pi so special? So is this is never ending. There's no repeat. Oh, you're right. We'll get there. So pi, right, 3.14 ... It goes on and on, but it's not repeating, right? And then I, that's an imaginary number. Okay, good. So we're going to tie that to rational expressions, okay? So rational expressions or rational functions, we just have variables in it. So we're going to use all the same rules as when we have fractions, okay? So there's one important piece to this, a number that can be written as a fraction, but no 0 in the denominator, right? That's one rule. So this one is not a rational number. 9/0. What? A lot. A lot. Okay, let's talk about it. Miss Wiz was a genius about this one this morning. I always talked about it with if you had 5 and you broke it into 0 groups, that's impossible, but this one's better. She said, well, if you had 5 free throw shots in a basketball game and you got 1, that'd be 1/5, right? 1 out of 5. But can you get 5 shots out of none? No, it's impossible, right? You can't get 5 shots when you didn't take any shots at all? Okay. I like it a lot. That's the best explanation I've ever heard, the best analogy. You borrowed it, and now I'm going to borrow it from you. Okay, forever. So this one was also borrowed. So NO is undefined. You can't do that, so it's got a 0 in the denominator, right? But if you have a 0 in the numerator, that's okay. That's borrowed too. I'm just very resourceful, right? No. I rarely do make things up all in myself. It's usually ideas from something else. It may be, right? What did I make up? I come up with nifty ideas, but it usually stems from something that I saw or thought about, or, you know what I mean? It's usually, what? I think everything stems from something, right? So never be afraid to build on something. Okay, moving on. Okay, so there's no need to get scared when we put variables in there, right?
No.
Because it's the same thing. So a rational expression is just a fraction. We call it a ratio of two polynomials. So that's could we graph that? Can you explain to me what that looks like graphically? Show me with your hands what it looks like. Fantastic. Where is it shifted? Is it shifted up above the x-axis or below? I love when we tie in the graph. It's just my favorite. Isn't it up high? Didn't it look like that? It was a reach. It's not working. Wouldn't it be up here? Like this? It would have imaginary roots. Good job. You guys are tying it all together. And then this one, what's this one? That's just a line. So what we're saying right now is if I take this and divide it by that, I wonder what we would get. I don't know. Okay. All right, so here's all of our parent functions that we've done so far. Rain, can I get you to shut that for me, please? So here's all the parent functions that we've done so far. Does anybody know the name of this one? It is a line, but that's not the name of it. I like that word, linear, but that would be this one. This is a linear function. Good job. It's a constant function. Why can't I give her candy? That was good. You're welcome. Are you guys being complainers? Haters? Okay, what about this one? Absolute value function. Because that one's a little bit more common. The constant one was the hardest one. This one?
Parabolic function?
It sounds good, but it's got a parabolic shape. It is a parabola. Quadratic. There we go.
What do you have today?
You're sick of this. This one's quadratic. Good. This one's cubic. That one's easy because we don't call it anything else, right? It's spelled kind of different. So there's something coming next. It's rational. Does anybody think they know what the rational functions look like? Miss Wiz, hold on. Miss Wiz did this with the whole function dance with you. Okay, Kayla, let's see. Is it the one with what? Yeah.
Oh, it's what
Like this? Right? Like the Egyptian. Right? Good job. I think she should get candy too. Okay. All right, so we're going to do a discovery activity based on rational functions. So what I want you to do, listen up, everybody listen up. I want you to do 1 through 10 and I want you to graph them, but I want you to think about the transformations as you are graphing them. Okay? So, don't just concentrate on graphing, but concentrating on what is occurring in the graph. Okay? So we're going to do 1, 2. If you would like to answer the questions, that would be great, but some in the other class, they were just trying to graph them. I don't want to go through these. Okay. So, first thing I need you to do is graph them and think about how they are changing. Transformations, okay? Let's pause this. Okay, so let me give you guys a little clue. So there's one very important point. Can anybody find the point, Michael?
Oh.
1, 1. Why? Why is it doing that to me? Okay, there we go. It's 1, 1. And is there another point, Florencia? Negative 1, negative 1. Good. And then we just draw our shape. They are asymptotes, Florencia. How do you know?
Because they don't touch the x-axis.
Very good, Philip. They are asymptotes.
And we know that they never touch the x-axis. I already said that.
Okay. So I guess for number 3, we could say, at what point do the graphs intersect the x-axis? Never, because the x-axis is an asymptote. Okay. All right, guys. And guess what? This one has asymptotes in the same spot. You guys keep going. Recording. Okay. So some of you asked me, how did I know it was at 1, 1? Well, if I go over, isn't 1, 1 an actual ordered pair? And an ordered pair represents an x value and a y value. So if I were to put 1 in for x, wouldn't I get y is 1? Okay, we could do that for each one of these points. Right? I could have a table over here. This is how you do it at old school. All right, so I know it's 1, 1. I know if I put in negative 1, I'm going to get negative 1. If I put in 2, I'm going to get a half. So if I go over 2, I'm going to get a half. If I put in 3, I'm going to get a third. If I put in 4, I'm going to get a fourth, right? And it keeps going like that. That's how to graph it old school. We're not going to graph it that way, but you can always check to see if your reference point is correct that way. This one was the same, right? Only it's a reflection over the x-axis. So instead of starting over here, over 1, 1, I went over here in the negative direction. So that one's done by just using the parent graph. So the answer to this one, how are the graphs f of x and g of x similar? How are they different? They're similar in shape. They both have the exact same shape, right? Same shape. And their reference point is also the same distance away from asymptotes. Reference point, same distance. It is in a different location, but it's the same distance, right? I'm exactly 1 unit away from the vertical asymptote, and I'm exactly 1 unit away from the horizontal asymptote. All right. So that's what you were supposed to graph. This one's our parent graph right here. And this is our parent graph, and then the graph of when the function is negative and reflects over the x-axis. Okay, moving on. Looking up here. Reference point, a point that describes the relationship between the horizontal asymptote and the graph. I say the relationship between the horizontal asymptote because when this reference point is going to move, it's actually still going to stay 1 unit away from the vertical. It's only going to change on its distance away from the x. And the reason for that is, Parsa, do we need to move? Something going back there? No, I'm just wondering. So the distance away from the x-axis is because when we're trying to find something, don't we always substitute in for x? And that gives us our y. So our input is our x and our output is our y. So that's why this distance is going to change. If anything changes with the reference point, it's going to be away from that horizontal asymptote. Okay? All right, let's move on. So I'm going to graph these without Desmos, without using any type of table. I'm just going to do it by using transformations. And what I'm going to start out doing is I'm just going to use the asymptote first. So I'm going to say to myself, I know that my vertical asymptote is going to be here, and my horizontal is going to be here. This one, my vertical asymptote is going to be here, and my horizontal asymptote is going to be there. And just take a moment and try and figure out how I knew that by just looking at those equations. Okay, show me with your hand if you think you know how I got it. Okay, so I've got about half of you, looks like. Okay, so now to do the graph, my reference point, like I said, is always going to be 1 unit away from the y, and in this case, it's also going to be 1 unit, from the vertical, and in this case, it's just going to be 1 unit away from my horizontal. So I've got 1 there, and 1 here, over 1, up 1. There it is there. No graphing software necessary, no table necessary. Over here, same thing. I'm going to go over 1, up 1. There's that one. And over 1, down 1. There's that one. So I'm really, in this case, only concerned with the asymptotes. For those of you that didn't see it, this is why there's asymptotes. Okay, remember in the very beginning when we said that you can't have the denominator 0? So this number right here, this whole thing right here, cannot equal 0. Well, just like we've been doing with everything else when we're doing transformations, don't we set it equal to 0? Can't equal 0? If you add 1 to both sides, it can't equal 1. Right? So just like when we were finding our zeros, and I would give you this, x minus 2, x plus 1. Right? And I say, what are my zeros? You'd say 2 and negative 1. Same idea. Right? So if x can never equal 1, that would make sense why I've got a vertical asymptote here. Right? Because so I can never have an x value at 1, and that's why the graph bends right there. You see it? Bends right here. Because I can never have a point on that line right there, ever. Because of that. Because it would make my denominator 0, and then it would be undefined. So it's going to skim it. So what would happen if I did this? It would be on the other side, right? I asked them so it would be on that side. Okay? Right, yeah. It would just be, the whole thing would be shifted over a little bit. Do we want to do it? Actually, the whole thing, let's see if I can do this. The whole thing would shift right there. This was calls it whiteboard magic. What? Smartboard magic. Okay? So what's the 2 doing? Not where the x-intercept crosses, but where the horizontal asymptote, how it's translating, right? So it's going up to. When we were back in, when we started with absolute value, didn't we write it in transformational form like this? I'm just going to cover this up really quick. We wrote it in transformational form like this. Because this is really the y. So now, if you want to know this shift, it's 1, and this shift, it's 2. You can look at it like that, or you can go back to just this. Right? That this is your 0, and then this is a shift that's up 2, whichever way you want to look at it. Okay. There's that. Now, this one's where it gets really cool. All right, so I only have a horizontal asymptote at where x equals 0, right? There's one here because there's nothing shifting it in that denominator, right? There's nothing shifting this one over, and there's nothing shifting this one up and down. No vertical shift, no horizontal shift, right? Same thing on each one of these and each one of these. None of them have a horizontal shift, and none of them have a vertical shift on the asymptote. So I'm going to color code these. This first one is my parent graph, 1 and 1. I'm just going to use my reference points. I'm not going to make a graph right now, just so we can see it, okay? This one's also 1 and 1. This one is still 1 away from the vertical asymptote. But remember when I told you the only thing that was going to change was from the horizontal asymptote? It's going to be up 2 and down 2. And this one's going to be up, what do you think? 3. 1, 2, 3. 1, 2, 3. This one, same thing. 1 distance away from the vertical, but what do you think it's going to be going away from the horizontal? Anybody? It's going to be a half. And this one's not going to be a half, but a third. If it was on a test, you'd be so mad. Why? I'm going to show you why you're not going to be mad at all. Okay, so now I can draw my graph. There's my parent graph of 1 divided by x. Now it's kind of looking messy. And this one kind of goes, it skims right next to the asymptote. This one's pretty even. But this one, if you notice on the Desmos, it's really close when it's next to that vertical asymptote, and then it kind of gradually makes its way down. Did you guys notice that? Okay, I'm going to show you just a couple more things before we move on. So I would rewrite this one. Like the T of x, I would rewrite it like this. Isn't it twice 1 over x? Because it jumps up, the reference point jumps up 2. And this one over here, we could rewrite it as 3 of them. And this one here, I would write it as 1/2. Isn't that the same as this? If I multiply straight across, isn't that 1 over 2x? So it's just like pulling out a half. I'm factoring out a half. So over here, I would factor out a third. Okay, final question. How could I, for sure, and it's a test, I want to double check that I'm right. How could I check that I'm right on this one right here? So say you don't have Desmos, you don't have a calculator, you just have a paper and pencil. How could you check? Kristen, what would you plug in? Numbers. What numbers would you plug in? You would plug in the reference point. So if the reference point on this one is 2, 1, the red graph here, if the reference point is 2, 1, I could check it by plugging it into this graph, substituting it back in. So y equals 2 over x. What's x in this ordered pair? 2. Is 2 divided by 2 1? So is that the reference point? Yes. Okay, got a challenge for you now. Isn't that pretty? Okay. Can you work in reverse? If you know your horizontal and vertical asymptotes, and you have a reference point, can you come up with the equation? Work with your table group. Let me see you do it. Okay, so you guys are going to go, oh, that's it? Ready? Okay. So I'm going to work backwards. I'm going to say the first thing I did when I did these was I drew, oh, let's throw back. The first thing I did was I drew my asymptotes, right? First I was concentrating on the asymptote that was associated with x. So the one that was associated with x is this one, right? So x can never be 1, 2, 3. X can never be 3. Wouldn't that be written like this? Right? X can never be 3. Y can never be 1, 2, 3, 4. Right? That's exactly how you do it. Then we had to talk about the reference point and how far away it is from the horizontal asymptote. How far away is this reference point from the horizontal asymptote? 2. All right, let's do this one. Okay, so what can x never be? It can't be negative 2. If x can never be negative 2, then what must this be? Positive 2. Y can never be what? 1. So we needed to go up 1. What goes out in front here? How far am I away? How far is my reference point away from my horizontal? 1, 2, 3, 4. Now you can write it this way, or you could write it like this. That's the same thing. Or you could write this one like this. I should be using something different, but I'm not. They are the same thing. Where did I get what? I can't hear his question. Why did I do the 2 like this? This one? Because it's, remember when I said on this slide right here? Right here? 2 over x is the same as 2 1 over x's? That's where I got it. It doesn't screw it up, Dylan. I'm going to show you why. When you multiply these out, isn't this really 2 over 1? It's the same thing. Okay? All right, ready? I've got one more to show you. This is a homework problem. So, guys, this is the form we wanted in right here, where I've got x minus h, where h is that horizontal. It's actually a vertical asymptote, but it's what x can't be. And k is what y can't be, right? And then a is how far of a jump we're going from that horizontal asymptote. It cannot. That's what we're finding. Okay. So, I'm not going to do this one. I'm going to do your hardest one in your homework for you right now, okay? Well, I can go. These are super fast, right? This is just shifted over to what? The right or the left? The right. Is there any shift for the other asymptote? No. And then I would just graph it. Super easy. This one, just keep going. Okay. Here's the hardest one. Okay, on this one, it's not in this form. There's a 3 in front of that x. So what could you do? I just heard it. Factor out of 3. It's exactly right. So look what happens. So then how far away from my horizontal asymptote is this shift going to be? A third. That's the hardest one on the homework. Everything else is easy? Okay, let me get you your homework. Good job, guys.